Marom Bikson is a professor of biomedical engineering at the City College of New York and co-director of the Neural Engineering Group at the New York Center for Biomedical Engineering. He's known for his work on brain targeting with electrical stimulation, cellular physiology of electric effects, and electrical safety. Bikson co-invented high-definition tDCS, the first non-invasive, targeted, and low-intensity neuromodulation technology. We are thrilled to have him here with us today. Welcome, Marom.
Thank you, Lisa, for the invitation. And over the next half hour, I just want to share with you some thoughts about how digital healthcare, how wearables might affect how we do neuromodulation, how we apply brain stimulation. So these are my disclosures, and these slides and references are already online. So starting with the definition, what is neuromodulation? Broadly speaking, it's the intentional application of energy to the nervous system with some purpose. So that purpose could be to improve people's mood if they suffer from depression. It could be to control seizures if they have epilepsy, and it's also increasingly applied to healthy individuals. So this is to increase human performance, and often that energy takes the form of electricity. So we'll say brain stimulation or electrical stimulation. And so there's many forms of neuromodulation, many kinds of technology. They're usually named by the way they apply energy to the nervous system. So for example, deep brain stimulation will have an electrode that's implanted deep in the brain, and we'll be applying electricity to these deep targets. Spinal cord stimulation, transcranial magnetic stimulation uses induction to produce electricity inside the brain. Electroconvulsive therapy increases the stimulation intensity until a seizure is produced. And then you have a class of technologies that are broadly called transcranial electrical stimulation. These are low-intensity, 9-volt battery device type technologies, and one of them is transcranial direct current stimulation. And generally, you can sort of classify these as technologies that require surgery. There's something implanted. Technologies that require you to come into the hospital. For example, if it's electroconvulsive therapy and you're producing a seizure, this needs to be done in clinic. And then you have these other technologies which, for the purpose of what I'm talking about here, I'm calling them wearable. These are the caps that you can put on your head, while you watch the Patriots, and it'll do what it needs to do. And I wanted to focus on them, and specifically on one variant called transcranial direct current stimulation, or tDCS. Maybe some people in this room have already heard about tDCS. I think as far as investigational, interventional technologies, this is the most explored technology right now. There are multiple clinical trials published every day, meaning by the time you come in here, to the time you leave the door, there'll be 3 more papers we all need to read. This is what it looks like. You can sort of see here, there's a small battery-powered handheld device, 2 wires that come up to a headgear, and in that headgear are some electrodes. So the weak direct current is being pushed up by the device and through this person's head. A typical session will last tens of minutes, and most people will be feeling like a tingling. I tend to experience itching. And tDCS is a powerful modulator of brain excitability, and it's also a modulator of plasticity. And because of that, it has been explored for many things, sort of you name it, of neurological and psychiatric disorders. It's being tested. I should say it's currently not FDA approved here for any indications. It is approved internationally. And as I mentioned, there are many, many trials. And because it is a 9-volt battery device that you wear on your head, this can go home onto a regime we call remote supervised. I don't have time to unpack more about tDCS, but I want you to refer to these papers that describe really decades of mechanistic studies. I like to say direct current stimulation is the original LTP. We know this is a modulator of plasticity. It's considered very safe enough to use on healthy individuals, in fact, and there's lots of guides on application. Now, when we started to look at tDCS technology about a decade ago, all tDCS was applied with 2 very large electrodes placed on different positions on the head, 2 large pads. We developed the first high-resolution MRI-derived models of transcranial electrical stimulation. This is my MRI linked to my model. And we use these models to predict how current flows through the head during tDCS. So basically what brain regions are being stimulated. And what we found, which is maybe not surprising in retrospect, but at the time was controversial, that when you put two large pads across the head, you don't stimulate just one brain region or just one node. You stimulate diffusely. You're basically stimulating a large network when you do tDCS with large pads. So instead, we proposed something we called high-definition tDCS. High-definition tDCS, or more generally high-definition electrical stimulation, uses smaller electrodes. That's the key distinguishing feature. Once you have smaller electrodes, you can first of all put them closer together, and you can also deploy them in different kinds of configurations. What you're looking at here is the 4x1 configuration that produces focal transcranial stimulation. So now this array can be moved around the head to target different cortical regions. More broadly, we proposed software that allowed you to select a brain region, either sort of on a generic model or in an individual model, and that software, this algorithm, would automatically prescribe the optimal place to put electrodes on the head and how much current to put into them in order to target this brain region. And this was done in a closed form kind of way, subject to certain constraints. Or another way to think about it is if you already have a cap on your head and it's preloaded with all the electrodes, and those electrodes are connected to a little stimulator in a computer, that computer will optimally guide the right amount of current to each one of those electrodes to stimulate a particular brain region. And because all this has been published and also productized, because we think that this targeting is solved in that sort of numerical sense, where a lot of our interest has been focused on since then is not how to target, but what to target. And so this brings me to this notion of personalized neuromodulation. But just to point you to some of the key papers that established focal non-invasive stimulation, it was a lot of work to create these small electrodes to deliver stimulation that was tolerated, as well as some of the optimization and validation. All right, so personalized therapy, what do I mean by that? By that I mean that you have a patient and you take some sort of measurement. It could be a scan. It could be sweat we heard about today. It could be a blood draw. And that information is then used to inform a decision, a treatment decision, about what that individual would get. And ideally, this could be done iteratively, so that now you can see how that particular intervention, that therapy, changes that marker, and then you would refine the intervention iteratively. So when I'm thinking of personalized therapy, I'm really thinking about iterative therapy. Ideally, what would you like from a personalized therapy in the sense? First of all, you want it to be tunable. You want it to be able to change it on the fly. You want, if you're thinking about this loop, you want that loop to have some sort of reasonable time cycle, not 10 years for one loop. And you want minimal risk as you're actually tuning the intervention. And so if you look at the kind of options you have available to you, well, I mean, obviously all drugs, all molecular therapies are to some extent personalized, and that you pick the one that you think will work. But it may be difficult to change the formulation in that pill box on a daily basis. And also we know with chemicals, a very small change can have very profound impact as far as safety. So there's limitations there as far as anything that's implanted or anything that requires you to go to the hospital. Again, it's obviously another very promising area of personalized medicine, but harder to imagine how this loop would work on a continuous basis. Everyone's very excited about the potential for therapeutic apps. Though there are many severe neurological and psychiatric disorders where it might be very hard for these apps to have a big impact, and of course I'm steering you towards maybe wearable neuromodulation, transcranial direct current stimulation is a great candidate for closed loop stimulation because it has these features. Okay, and so now I want to talk about this notion of targeting and how do we actually then pick which target we're going to go after. One idea we and others have been very interested in is to use image-guided stimulation, and particularly EEG. So EEG, it actually looks a lot like high-definition tDCS. It's a cap with a bunch of electrodes in it, but what those electrodes are doing is they're recording the electrical activity produced by the brain. And there's a very long-standing idea called reciprocity, where you can take those potentials that you're recording on the surface of the scalp and are being produced by a particular brain region, and you can somehow invert them through a principle of reciprocity, and then stimulate back into a different set of electrodes in order to stimulate that region again. This idea in itself is actually rather old. We've recently applied some modern simulation techniques to, I think, again, produce a closed form solution. And again, now we have activity-guided stimulation. I'll show you one example of how we applied it. This was actually a trial we ran right here, not too far away. It was run at Spalding. This was for severe fibromyalgia pain. These are patients who are refractory to drugs, and they came in for daily, so repeated in-clinic sessions, and this is what we did to them. Ironically, though we were treating pain, we started with painful shocks applied by a thermode. This activity would be transmitted to the brain and produce a very profound response in the brain, essentially the brain's response to the pain, that we can record with an EEG system. For each patient, for each day, we would then invert that EEG to provide them a personalized stimulation, and we would immediately assess how the EEG looks afterwards. So we weren't just interested in affecting their self-reported VAS, their pain score. We're actually also interested in normalizing their pain to a more normal response. And so that's what you're seeing here. So the trial was successful for those patients who completed the series. It took about 2 weeks, and our goal was a 50% reduction in pain. About half the patients did not complete. And this picture is really the reason why. So this is, I mean, I grew up in Boston, so this is your winter right here. These patients have severe fibromyalgia. I mean, they can barely shower in most cases. It's hard for them to dress themselves. They're in so much pain. For them to have to drive to Spalding, park their car, trudge through that. Again, this was all in session, and so obviously that was a major impediment, despite the promise, for them to come in. And obviously this sets up the idea of, okay, well then why not go home? Because this technology can go home. So I want to talk about that. These are just some references that you can look up as far as how to use the EEG to target, and also this one particular trial. So personalized neuromodulation at home, there's some sort of doctor, he's sitting in the cloud, and then he's pushing down into your handheld device your tDCS therapy for the day. All right, that's sort of the big picture idea. And how we're implementing it is sort of unpacked here. First of all, we're monitoring and recording from the subjects in 3 different ways. We have sensors on the headgear itself. So that means that when they're actually applying the stimulation, they put on the headgear. That headgear can have EEG into it. It can have FNIRS in it, galvanic skin response, a whole bunch of sensors that could be very high quality data, but only when they're stimulating themselves, right? So that limited 20 minutes a day. We've also been developing and exploring the use of medical wearables. So this is now continuous data, and also our own kind of apps, or actually interface software that I'll unpack. All these 3 measures are then being fed to a clinician who's downloading this data from the cloud, who's making a treatment decision, both on what they're seeing immediately from that patient, but also the historical record from that patient, and then the historical record from the whole patient cohort, and then they're pushing down a new stimulation for them to apply, and then again, the assessments are made, and so this loop is repeated. I want to talk a little bit about the questionnaires, which is a software, a GUI we call Electra, and the key, I think, distinguishing feature here, or the key lesson we learned, is that these questionnaires are adaptive. So when we started this, we started with what you think would be the rational thing, where you ask everyone the same thing every day, and you keep asking them the same questions over and over again. What we're looking for in our questionnaires is not a diagnosis, and it's actually not even necessarily an outcome measure, that we can have those, like pain reduction, that we can cake those in again. What we're looking at from our questionnaires is the ability to select between treatment options, not just 1 and 2, but really almost an infinite variety of treatment options. So the questions that we want to push to them are the questions that provide us the most information about selecting between different treatment options. Those are the questions that have the most value. And we found that when you ask people the same questions every day, how much does it hurt, how much does it hurt, how much does it hurt, those questions actually end up having very limited value in selecting between different treatment options. In fact, we found they just had a lot of limited value in general. People often end up answering the same thing all the time, or they get sick of answering, or the questions themselves irritate them. So rather, what we've been doing is we've been developing adaptive questionnaires. And those start with some very generic questions, and then based on how they respond, we move on in different ways down a tree. So we usually start with a very generic question. This is like our classic how we start, like the how are you? And let's say they say, well, today I'm doing bad. Then the software may say, okay, let me try to figure out why. Tell me, are you anxious? Are you sad? Do you have pain? Where is the pain? And so this is the kind of tree of information that you're collecting. And every single day, it's going to be a different series of questionnaires. We also found that sometimes throwing in what might seem like a bit more oddball questionnaires, like how's your family life? How was work today? Sometimes those questions themselves can give us more information or more insight at least about making a treatment decision, about deciding whether you should go left or right, option 1 or option 2. And that was a very important lesson for us. Talking a bit about the headgear and the medical wearables, we've heard a lot about that today. We've spent a lot of effort developing some of our own as well. And as I mentioned, there's 2 types of sensors we have. Some are on the headgear themselves. This tends to be higher quality data, but we only have access to that data during their session, so about 30 minutes between applying the headgear, doing the stimulation, and taking it off. And then we have our own wearable as well. And I want to hear the word to remind myself, this is responsive, so it's not simply just passively recording what they're doing. During stimulation, we're applying stimulation, and we're immediately seeing how heart rate changes. We're immediately seeing how EEG changes. We immediately see how blinking or galvanic skin response changes. So it's not just passive recording, it's responsive. And here again, the value to us is not strictly diagnostic. Right? It's actually the value is in selecting between different treatment options. That's where we see the most value, and I think as a result of that, how we design the technology and how we design the algorithms tends to be a bit different because it's very much focused on this mission. So as I mentioned, we have the wearable, this dot, and we also have the headgear. And here things get complicated because we can take that data and we can convert it into some like reduced metrics that clinicians are used to seeing. Heart rate, spike rate, and so on. And so now the clinician is seeing that on a GUI, and you might imagine, well, now can the clinician use that information, this sort of aggregate, this is how much, this is their galvanic skin response over the course of the day. Can a clinician use that information to decide between treatment options? And our experience was this is extremely hard for them. It's great to have that GUI. They love to share that information with the patient. Here's your heart rate over the course of yesterday. But as far as actually how to take that information and incrementally tweak an interventional strategy day after day after day, I mean, that would be hard for anybody. And so it ends up being very difficult for them to use that information. Alternatively, you can just stick to the raw data, the big, messy data that's coming in from these devices, and you can try to train algorithms to make this sort of treatment decision on its own. In this way, you're not throwing anything out, and of course, they'll give you something, right? Because you're forcing them to make a decision one way or the other. And of course, the vision is that these algorithms could get smarter and smarter, both on a patient-specific level and looking on an aggregate level. But to do that, you have to be comfortable, as we heard before, you have to trust, right, an AI or some sort of machine to give treatment to people who in many cases are at the end of the line, right? They're suicidal, right? They're suffering extremely, and we're not quite there yet. And so really what we're doing right now is we're taking that raw data, we're using that raw data to make predictions, but you still have that clinician or that researcher who's sort of the stopgap, and ultimately they're the funnel. They're making the decision at this point. It's not a fully closed system in that case. So this was sort of the big picture vision that I showed you, where we have personalized medicine in the sense that there's constantly measures being taken from the individual, and those measures are being used to inform a decision that's then being used to pick a therapy and apply them. And I think some of the themes that I tried to convey to you in a very big picture view today is, one, we're looking for things that are fast and things that are iterative, and this is where non-invasive neuromodulation is extremely well suited. We want the intervention to be tunable and targeted. We want to be comfortable daily changing the intensity, the frequency when we apply it, and we want to feel comfortable that even as we're making these changes, we're not introducing any kind of safety risks, any kind of tolerability issues. And again, non-invasive neuromodulation allows you to do that. So that in a sense is that part of it is actually solved. The technology is already there. The hard part is, well, what do you do with that technology, right? Where do you guide the current on Monday? Which brain region should you stimulate on Tuesday? Should this patient get more? Should they get less intensity? And this is where these measures are coming in. And again, I think where maybe thinking about this in terms of the outcome, which is making neuromodulation decisions, may change how you design technology. It may change what you value as far as algorithms, because again, we're trying to make treatment decisions. So first of all, this is a responsive measure. We're looking at adaptive questionnaires. And again, we're very interested in the use of raw data. All right, so final point about personalized neuromodulation. So I've showed you sort of this rubric of how we've liked to do things, and we've deployed components of this into dozens of clinical trials. But I'll tell you, in every single case, we've had to tune things. And that's because when you're doing a clinical trial, the first priority is to serve the patients who are enrolling in that clinical trial. And while you'd like to keep everything always the same, right, because this gives you the most possible information to train your algorithms and to improve your process, that's never going to be the case. And in every case, what is available to you, what is ethical to do, will vary. And so these trials span the extreme of age from 2-year-olds who have had nonstop seizures since the day they were born, all right, to 80-year-olds, all right, and the other extreme of age, who are just looking for some quality of life, them and their families, some reduction in pain, some enhancement in cognition, to everything in between. So we're looking at this for epilepsy. We're looking at this for people who've had strokes and are looking to recover function. We're testing these kind of technologies, as I mentioned, for a broad range of neurological and psychiatric disorders. And at this point, it's not all closed. At this point, there's still a huge amount of human intervention in all cases. But as I tried to explain to you, it's ultimately going to be too complicated for any one person to make these decisions, right? If it's because it's personalized, I believe, that we need to bring in this automation. And very briefly today, I've just tried to kind of explain to you the directions that we're pushing in to make that possible. So thank you for your attention. Yeah, and the question in the back.
Is there any application of this for any kind of sleep disorders? Are you familiar with? I mean, it seems like the range of this is expansive. Have you seen anything going on in the sleep?
So there have been several trials looking explicitly at transcranial direct current stimulation, or actually a variant of it called transcranial alternating direct current stimulation, where the stimulation is phased in and out, almost like a slow wave. And this has been applied during sleep. And this actually has been produced some very controversial results. Some of them have been published in Nature, some of them have been refuted, which claim that stimulating during sleep at particular frequencies can boost endogenous sleep rhythms and then lead to outcomes afterward that would be suggestive of some sort of, well, in this case, it would be actually in healthy subjects. This was looking at memory. And so it is possible to apply this during sleep. We haven't done too much of that work. I guess because the reason you're asking is obviously many disorders, people also suffer from poor sleep, or in many cases, poor sleep is believed to be a cause of things like accelerating cognitive decline. So it is an outcome measure. It is something that we're looking at. Maybe this is part of this bigger idea is the way we're kind of approaching things, the way we're approaching questionnaire is traditionally, you take a patient and you lump them into a particular diagnosis, and you take another patient and you lump it into a particular diagnosis, and then you're looking to treat some very specific symptomology based on some very specific questionnaires. Part of the reason this is so different and it's so challenging is we don't necessarily have to do that anymore. Someone could come in with fibromyalgia, but what's really bothering them is a lack of sleep. And now we're assessing that lack of sleep, and quite possibly maybe their pain doesn't move so much, but their sleep does improve. And being flexible in how we ask questionnaires gives us the power to capture that and to serve them in a way that maybe the traditional clinical trial model doesn't.